Now we are at a point where like I'm going to tell you a little bit of what I have done in my graduate studies in my research. So I wanted to solve in an area where that can handle online changes of the ego vehicle environment. What do you mean by online changes? Like you have taught the model certain set of principles it is supposed to follow, but then it goes and the vehicle has entered into a new scenario which it has never seen before. But if you teach it while it's doing the planning while it's planning, okay, it can come up with certain trajectory where it avoids that pedestrian, it avoids that hitting that car. But you have set it and you have given a path, you have given a plan for the car to follow, and then you give it. But later when it comes to the corner cases, it breaks. Sometimes, like, there's an interesting problem called time scale collision cone problem. In a basic level, the problem with that is when there is a static obstacle which is sitting on the road, the car goes and it stops. It indefinitely stops. It doesn't do anything. It cannot go forward, it cannot take left, take right. So that's some of the problem with offline planners. Now the online planner which I'm going to discuss, the model predictive control, it's something which can take care of these scenarios while the car is driving. The offline planning is called the act before act before thinking. This is called, online is called act while thinking. You keep on thinking, and then you keep on sending the controller the set of inputs that the controller needs to receive, and then you plan the path accordingly. Then I wanted to go read this system, which can take the feedback, it can replan the trajectory. The model predictive control is a unified approach which can handle this constraints as well as the cost function. Like it can listen to what the car is supposed to do. At the same time, it can listen to what the car is supposed to not do and follow. I hope I was clear when I said that. So this model predictive control is something like which is a very interesting concept that is going to tackle that particular set of problem. Then I went and studied. So I'm just giving a rough idea of what model predictive control is like. So initially you have you start with certain guess velocities. Now let us this is a very specific problem. I'm just taking this example to give a rough idea of what an MPC algorithm, what we are going to see is. So you have a certain set of guess velocities. These guess velocities can come from an initial optimization scheme, or it can come from initial machine learning model, that has a rough idea of what velocities the car can take. Or a very experienced engineer, he can say that, okay, we can start with this amount of guesses, this velocities, and you can start with this set of accelerations. To start with guess velocities, what do I mean by guess velocities here is these are the set of velocities that the car can take. Now we have certain set of guess velocities that the car is supposed to take. Now what we do is we start with the planning, we start with the prediction, we look forward into n time steps. Here n time steps mean I want to look into the future. The algorithm itself is model predictive control. So we have a model, and we are going to predict how the environment is going to act. So we assume that the obstacle is going to travel with certain velocity, the ego vehicle is going to travel with certain velocity, and how are you going to avoid this set of collisions. So that we tend to predict. So we predict for n time steps, that is called a horizon, that's called planning horizon. You plan for a set of horizon, and then you give a certain set of waypoints. These waypoints, where the waypoints is something that where the car is supposed to go, that is obtained from the mission planner. This is where the car is supposed to go, and this is the state where you have obtained based on the motion model which you are working with. And finally, this optimization scheme is going to give you with certain set of velocities or angular velocities which the car is supposed to take in order to reach a particular goal. Say it's traveling from A to B through 100 points. You have given 100 points where the car is supposed to touch those 100 points and finally reach the end point. Yeah. And finally, we come across this control part, which is where you have planned with certain set of velocities and angular velocities, and finally you have controls for, say, you send it to the controls, like say 10 velocities or 20 velocities for specific control horizon, and then you let the car go with those velocities, and then you wait and see, okay, I have traveled for this control horizon, I have planned for a planning horizon, and now how is the environment going to change? So you plan, and then you send the inputs as a feedback, you loop it as a feedback, and then you keep on re-optimizing over the entire path the car is supposed to travel. This is a rough sketch of model predictive control. Uh, yeah, like don't worry if you like if it was if it's too, you know, difficult at the first attempt to understand, because it's a complicated problem. It involves different set of heuristics, different set of assumptions, and you know, it's a very interesting, very nice problem which we can tackle, which we for different set of you know, scenarios which we can use. So we can read a lot about it. There's a lot of literature out there. So yeah, I just wanted the whole you know, intention was to give a rough idea of how the algorithm is going to perform. Yeah. So this is the research I have done with respect to the model predictive control, and considering the actuator dynamics. And we have had an opportunity to present this in American Control Conference in Philadelphia. So what we have done in this model predictive control, for we have used this model predictive control for actuator dynamics. So I'll give a little premise over how the problem came to us. So we were using Mahindra E2O in our lab. Then the professor one time came to us and he told, you know, the Mahindra E2O, it is facing this problem. Like, you want the car to go at certain velocities, but it's not reaching that particular velocities. The controllers are fine, the planning is fine, but there is some set of uncertainty that is happening in between, which is not capturing, which is not making the controller to be more faithful. So that is the problem we saw. Then we started reading much of, then by the time we were reading much about the model predictive control. So we tried to use it, and the way we wanted to use it is we wanted to use it in a data driven fashion. Like, we don't want to go into different levels or different layers of dynamics. We don't want to analyze each wheel slip rate or other gear ratios or other things. So what we have done is we have given a set of data for the car to travel, and then we have captured the data, and we try to fit a first order model for that data, and we have included that in our optimization itself, in the model predictive control. In the cost function itself, we have included that, so that the cost function, whenever it is going to command that velocity, it keeps in mind of what all velocities that the controller can perform. So now my planner has become intelligent in a way that it understands, okay, controller has this fault, or there is some uncertainty in this system. Now I have to I have to plan the path in such a way that I have to plan the trajectory or velocities in such a way that it takes care of those uncertainties, and finally the car should reach the position with the velocity it is supposed to reach. So I have given the premise. Now this is a simulation what we have done in the car sim. Blue vehicle represents the ego vehicle. Ego vehicle, again, it means the car which we are driving. So this was initial MPC. This was normal MPC without our model, without actuator dynamics involved. And this is an intelligent MPC, whatever we have done, the blue car, where we have, you know, I told you, right, we have fitted a first order model into the objective function, and we try to get the velocity so that it is aware of what is lacking in the controller systems. And yellow represents the other vehicles on the road. And when you see the video, you see that the cars are overlaid. The overlaying is in order to show that, you know, there is a difference in the cars. You know, show the difference between the normal car which has normal MPC, whereas the car with intelligent MPC. So I wanted to showcase the difference between the performance of the two cars. So that's why I have overlaid. Yeah. So the first case is occlusion during overtaking. Or occlusion during overtaking is, it's like, suppose you wanted to go into another lane, or you wanted to overtake the current car, but you, when you're trying to overtake, like, you go to the right of the car and you want to come in front of the car, but when you have overtaken, you saw that, okay, there is one more car in front of the current car. Now how do you avoid that? We're going to see. See, in this case, the car with normal MPC, it has maintained 0.6 meters of difference, which is which it has almost come into a collision range. Whereas the intelligent car, it has maintained a difference of like 1.73 meters. So we are at a safe distance when compared to the model without this actuator dynamics. And second scenario is the lane changing scenario, where you want to move from a low speed lane to a high speed lane. There is a high speed vehicle coming behind you and you should not enter into the collision range. So the desired behavior here is the car has to accelerate faster, and it has done that. It has maintained safe distance. Now this is an interesting scenario. This is a sudden braking scenario where the lead vehicle, suddenly brakes while traveling. Now how do you maintain the safe distance? And you need to maintain the driver comfort as well. Like, you should not suddenly brake so that the driver feels the jerk. So you need to maintain the safe distance and ensure the driver comfort. See, the ego vehicle has maintained a distance of approximately car length. This intelligent MPC has maintained a distance of a car length when compared to the normal MPC. Yeah, you can see the differences in the velocities. Like, it's a much deeper discussion if I go into different models which we have implemented in this. Now, when the vehicle suddenly is cutting into our lane, now how do you decelerate such that you don't know, like, the car is still in your control? It has not gone out of your control just because there are residual velocities. This is an interesting plot. You can say, like, since we have used a data driven model, where I said we have fitted a first order model. Now like, you can ask, like, how can you like, why didn't you go to a very complicated model? Why don't you fit the data properly? So we tried that. We went to a higher order model and we used the radial basis function, which our data looks like radial basis function, and then we have used it MPC over it. We have seen a marginal benefit when compared to fitting a first order model. This is one example of using model predictive control and improving the driver comfort, or you improving the maintaining the car uh, far from the collision range. The reason why I have given my research example is uh, the field is still in research, is still in research mode. Like, when you go and listen to the talks which are given by Serta Carmen, or Peter Abil, or many Zoox engineers who are working on the autonomous car from ground up, like, from they are not adding. There are two things, like ADAS and autonomous driving. ADAS is something where you fit the current car with autonomous driving features. Like, you want a warning when the car is changing the lane, unintended lane change, you want a warning. And you want a collision warning, like, the car should tell us, like, if you maintain this particular speed, you're going to hit a vehicle. So there are different features that are augmented to the current car, that is ADAS. And there is one more product which is being developed, which is called autonomous driving vehicle, which is a vehicle from ground up, where the Zoox teams are working on. If you see the seats, that the seats won't face the road. They are going to face each other. Like, when you sit in that car, you're going to face each other. So that is the level they are operating at. And yeah, if you're interested, there are different levels of autonomous driving: level 1, level 2, level 3, level 4, level 5, 5 levels of autonomous driving cars, depending upon how much intervention that the driver has to put, like, whether the driver should act continuously, whether he should monitor. So level 4 is like, level 4 is a place where you monitor it remotely. Like, there are 4 5 vehicles which are running, and the person will be sitting remotely, and he'll be monitoring that okay, 4 vehicles, they have not entered into any emergency mode. Once there is an emergency mode activated, then it is going to alert this remote person that one of the car has entered into emergency situation, you need to give instructions. So that's level 4. And level 5 is complete autonomy, where you can even sleep in the car, and the car is going to take care of you. Yeah. So that those are the different levels the autonomous driving is operating, and there is different levels of research that are going at different levels of autonomous driving as well. Like many industries, if you see outside, they're operating at level 2 or level 3. If you see in that range, you see ADAS applications going on, and then there are some companies, some startups which are acting at level 5. You see Waymo acting at level 3.5, level 4. There are different levels that are operating. One interesting fact which I wanted to share is, like, there are around 500 plus startups around the world uh, in this autonomous driving field, because it's the obvious thing. Like, you have a calculator, you have an abacus, then you had to move on to a computer. Then you have a like a two-wheel mechanism, then you had to move into four-wheel mechanism, then you had to move on to the car. And now the immediate, the definite improvement in the car is making it smart, making it intelligent. So this is something that is definitely going to happen in future, and that's why many startups and many big players, if you see like General Electric, Intel, Siemens, Google, Baidu, these big players are interested in this, in realizing this technology of autonomous driving. And this is an aggressively hiring industry, and I'm interested to tell you that we are at a stage where the cars are still developing. There is still some amount of research which is going on, there is still some amount of product development which is going on in this autonomous driving. So it needs those people who are passionate, who wants to sit with the problems, who want to tackle them on a daily basis, who want to go through a different levels of refinement. So it wants those people, and it's asking for those people who are passionate, at the same time who are competent to tackle all these problems. And yeah, as I said, it's in early stages. They might be looking for a research engineers, some applied research engineers, some ML engineers, like who can understand. Like, that's the reason why I, in the initial level, I mentioned, like, if you go to a very specific products, you will act on a very limited level of domain. You will act in a very limited level of domain. There is any error in whatever you are implementing, there is a limited number of steps you have to go through. But when you come to this field, you have data coming from all over, and you need to give outputs, you need to give responses, you need to communicate all over. So you need to have a rough idea of where the systems are, what are the different levels that are operating. So you need to have a wide set of outlook. You need to be open to this multiple disciplines. So that's the reason why in the initial time itself, I have provided a hierarchy, so that that's an interesting you know place to start. Like, okay, what are we tackling, what are we supposed to do? So you need to have an idea. And then, what does a candidate need in order to come into this discipline? You need to be willing to solve the practical problems. Like, even if you work in a research lab, sometimes what we do is, like, we take a lot of assumptions, we handpick the results, and then we say that, okay, the model is working. But when you're building the product, and when you're taking it out on the road, and you're responsible for that product, like, tomorrow if the car goes and hits someone, you need to be like, if the car OEM is answerable for what is happening. So you have certain adventure, if I may say, in developing this field. So in working in this field, so you have to be able to solve these kind of practical problems while you're in this discipline. And then, as I said, there are two subfields, ADAS and AD, and this is projected to be a $54.23 billion industry in future. And as I said, the next obvious step is to go for automotive. And when we speak about the careers in general in motion planning, we have different set of careers. And if I want to go back to this hierarchy, if you see, all these blocks needs engineers. You need a sensor fusion engineer, you need an ML engineer, you need a perception engineer, you need a computer vision development engineer, and here you need a systems engineer. Then you need a motion planning engineer, you need a control engineer here. All these systems are demanding engineers, and uh, like they need people with knowledge and people with competence to come to that place. Yeah. So like this is a final note which I want to say, that the field is growing, it has many interesting problems to solve. You can come up with any skill set, there is a requirement. You come up with ML, you come up with optimization background, you come up with pure math background, you come up with interest, and that's the reason, like we need passion. The field is growing, so the faster you learn, the faster you equip your skills to this and be ready as an engineer, the companies are ready to take you in. That's my final note. Thank you from my side.